All right, so I'm going to do an ice table example for you. Now, typically I have my husband helping me record this, but today I'm on my own. I don't have a camera stand either, so I'm going to do the best I can to show you how to do this problem and get everything on the board as I go. So your ice tables, they are useful for determining concentrations of different species at equilibrium. And say we, are given a certain amount and we want to figure out how much of that species is present and the species it creates at an equilibrium. That's why we use ice tables. And most of the time, how I know that I'm going to be using an ice table to calculate the concentration of a species is I'm given a KEQ value. And I'm given the concentration of some of the species in the equation. So this one is a little bit different because it doesn't necessarily give us the concentrations right out, but it gives us all the information to calculate the concentrations. All right, so let's get started. At 650 degrees Celsius, the reaction below has a KEQ of 0.771. If 2 moles of both H2 and CO2 are placed in a 4-liter chamber and allowed to react, what will be the concentration of all 4 gases at equilibrium? All right, so just by looking at this, I know I'm going to have to calculate a concentration because I have 2 moles here and 4 liters here. That's not a big deal. I do have a piece of superfluous information, which is this 650 degrees Celsius. That does not affect our equilibrium at all. So anytime you're given a temperature in an equilibrium problem, just ignore it. All right, so the first thing I like to do is I'm going to go ahead and calculate my concentrations for the H2 and the CO2. You can do this before or after, it doesn't matter, but I just prefer to do it before. I'm given the choice to do it before or after. I would rather go ahead and get the easy calculation out of the way. So I'm going to do that off to the side here. The cool thing about this is these molarities are going to equal each other because we know we have 2 moles of the H2 and 2 moles of the CO2, and they're placed in the same volume, so we know that those molarities are going to be equal to each other, which makes the math easier on us because I only have to do 1 calculation instead of 2. So this is going to be the molarity for both the H2 and the CO2. So we have 2 moles over 4 liters, and that gives us a molarity of 0.500 molar. All right, so now that we have that out of the way, let's go ahead and set up our ice table. And this is just an easy way to coach you into being able to do problems like this. Now, when you do this over and over and over again, you won't have to set up this table anymore. But for the time being, I suggest practicing it on your problems, and probably for your exam, your professor will want to see that you know how to do an ice table. All right, so I'm going to go ahead and go ICE. I'm going to write all that information. So our I stands for initial, and that's just going to describe the initial concentrations of whatever we're given. The C stands for change, and this represents the change it will have to go through in order to reach equilibrium. And equilibrium is E. All right, so let's get started. Initially, what we just calculated over here, we know we have half molar of the H2 and CO2. So let's go ahead and plug those in. But what about the CO2 and the H2O? What are their initial concentrations? Well, we don't know their initial concentrations. That's the whole purpose of creating the ice table, so we can figure out their concentrations at equilibrium. So these guys start off at 0. Now, the change part is very important. A lot of people have a hard time grasping this. So I'm going to start out with half molar of each of these, and some of that is going to be converted into CO and H2O. I just don't know how much. But I can figure out how much by saying, okay, well, H2 is going to lose X amount to the products. CO2 is going to lose X amount to the products. the CO is going to gain X amount to the products. And the H2O is going to gain X amount to the products. All right, so say for example, we had a 2 in front of here. That 2 would have to go here because the stoichiometry of the problem. So if this were true, if there was a 2 right here, this would gain 2 times that amount from the reactants. But this is a simple one. Everything's in a 1-to-1 ratio. Makes everything nice on us. So it only gains 1x. Okay, so whenever we're doing our equilibrium part down here, all we have to do is combine the I and the C rows. So this will be 0.500 minus x, 0.500 minus x, and 0 plus x is just x. So I'm just going to say x down there. So now we can start calculating what these concentrations are going to be at equilibrium. So let's go ahead and write out our equilibrium expression, just so we have that off to the side, and we can refer back to it if we need to. So our equilibrium expression is always going to be reactants over products. So we have CO, concentration of CO times the concentration of H2O divided by the concentration of CO2 times the concentration of H2. And we were given in the problem that all of that equals 0.771. So just like in your other equilibrium problems, you're given a concentration for these, and you just plug in that number into these brackets. It's the same thing here. There's nothing different. The only thing that's different is we don't know what that amount is yet. So we're going to plug this X in for this CO, this X in for this H2O, this 0.5 minus X in for both the CO2 and the H2. So let's go ahead and plug that in. So we have X over 0.500 minus X, 0.500 minus X. And all of that equals 0.771. All right, I'm going to erase this because we don't need that anymore. We already recorded that. And I'm going to move all this work up to here. Need a bigger whiteboard. All right. So, all I'm going to do and to take my next step, this looks kind of sloppy here, so I'm just going to reduce some of it down. I know x times x is x squared. So I'm just going to x squared. And what's going to make your life a lot easier, since we're having squares and stuff in this, is to combine these, just like we have x and we put it to x squared, we can do the same for this. We can do the exact same for that. So we'll go 0.500 minus x, and that whole thing is squared. And all of that equals 0.771. All right. So now that this looks a little bit prettier, let's go ahead and solve for x. So I have a square up here and a square down here. If I take the square root of both sides, that gets rid of my squares. All right, so that means we have x over 0.500 minus x equals, and I'll calculate that out here real quick, 0.771, 0.878, 0.878. Okay. So now we need to start working on, now that everything's pretty and we don't have any more squares, we need to start working on getting x all by itself on one side. But we got to deal with this right here. We have an x on top and an x on bottom. But we need to get rid of this denominator because that's going to make solving for x a lot easier. There are a few ways you can do this. You can go the cross multiplying route, or you can multiply this over here, which is basically you're going to end up getting the same answer. Because, you know, technically this is over 1, and x times 1 is x, and then we end up multiplying that over here. So you can think of it as the cross multiplying route, but I'm going to think of it as we're just going to multiply the whole thing by 0.500 minus x. Now this is gone since I'm multiplying both this side and that side by 0.500 minus x. This is gone. And now I just have to take care of this. So we have x equals, and I'm going to have to distribute this to both of them. So I know I'm going to have 0.878x. Actually, that's going to be a minus, so I'm going to take care of this one first. So 0.5 times 0.878, 0.439. 0.439, and that's going to be minus 0.878x. So now we have 1x over here and 1x over here. I'm going to move this x over here because we want both x's on the same side. So I'm just going to add this onto that side. So we'll end up having, I'm going to come down here now. So we're going to end up having x plus 0.878x equals 0.439. All right. Now, a lot of people, when they get to this portion, they get confused because they don't know how to get rid of this 0.878. It is actually very easy. So we have an x here and an x here. We can remove that x from the equation. Basically, what I'm doing is dividing x and x, like that. So x divided by x is 1. 0.878x divided by x is 0.878. And all of that is equal to 0.439. Okay. So now it's very easy to get x by itself. This is going to end up being 1.878. All I have to do is divide it to right there. So our x is going to be, oh, that's convenient, I already have it in my calculator. So 0.439 divided by 1.878, 0.234. 0.234. So that is our x. But what we were actually asked is, what is the concentration of all 4 of the gases at equilibrium? So whenever we are figuring out the concentration of all of the gases at equilibrium, we're going to be using this C row here. So at equilibrium, the concentration of our water is X. At equilibrium, the concentration of our carbon monoxide is X. That's easy. We already solved for that right down here. So at equilibrium, concentration for our water is 0.234 molar. Concentration for the carbon monoxide is 0.234 molar. But since our H2 and CO2, we started with half molar, but we lost a certain amount because some of it was converted to the products. So we lost that X amount because that X amount was converted to carbon monoxide and water. So to find the molarity for the H2 and the CO2, we're just going to plug in for X right there. So for the H2 is 0.500 minus 0.234. That X that we just solved for right here. And that amount gives us 0.5 minus 0.234 is 0.266. 0.266 molar. It's the same thing for the carbon dioxide. So let's just not even bother calculating that. Let's just record that. So we calculated it just up here for that. 0.266 molar. So now we're at the end of the problem. We've solved for everything that we need to solve. Yes, they are messy. Some of these you will end up having to do quadratic formula, but you can easily avoid it by taking this step that I took right here, where I took the square root of everything because I saw I had a square on the top and a square on the bottom. That's how you avoid using quadratic formula. There are a few other ways that you can avoid using the quadratic formula by determining if this X is an inconsequential amount. I'm not sure if your professor has taught you that way yet, but if they haven't, just contact me and I can teach you how to do that as well. So I hope this clarifies how to use an ICE table for you. And really what's going to get you in these is the algebraic rearrangement. That will trip up everybody on an exam. So just take your time and make sure you are solving them appropriately. And also a way that that professors will trip you up on the exam is not asking for all of the concentrations. They'll only ask you for one. Either that or you'll get to the arduous part of the ICE table, which is this whole part right here where we're solving for X, and then you'll forget to report what the concentrations are. So just make sure when you get down here and you know X, make sure you go back to the question and be sure you're actually answering what the professor asked. So I hope this clarifies the ICE table for you. If you need any more help, don't hesitate to call me.